Nature has some physical magnitudes that are conserved over time. We have already seen that the energy of a closed system is conserved. We have also seen that the linear momentum in a collision is also conserved. We can use these conservation laws to study the time evolution of the physical system without knowing the details of the interactions, such as what happens right at the collision between a baseball and a bat. Conservation laws in nature are a very powerful tool and gives us a lot of information about the laws of nature. There is an angular counterpart to the linear momentum and the linear momentum conservation. We define the angular momentum of a particle in motion with linear momentum p as L equals the cross product of r times p. If the linear momentum is the quantity of motion of a particle, its angular momentum is the quantity of the angular motion of this particle. In the definition of angular momentum, r is the position vector of the particle. Of course, if we choose to calculate the angular momentum with respect to another point, this will be different. There is one angular momentum for each point we choose to calculate it with respect to. The angular momentum depends on the point that we choose. Let me express this angular momentum as m times r vector cross product v vector. Angular momentum is measured in kilogram times meter squared over second. Let's pay attention now at the cross product. The result of a cross product of two vectors is another vector. This resultant vector is perpendicular to both r and v. To calculate this cross product, we go from the first vector towards the second, and if it is counterclockwise, it will be positive, out of the paper. If r and v are parallel, the particle has no angular momentum. If r is perpendicular to v, the angular momentum is maximum in this case. Remember that the magnitude of the cross product can be written as the magnitudes of r times that of mv times the sine of the angle between r and v. So, for angular motion, we saw that the moment of inertia played the role of mass, the angular acceleration that of the acceleration, the torque that of the force, and now the angular momentum plays the role of the linear momentum when it comes to describe angular motion. Having this in mind, let me calculate the derivative of the angular momentum with respect to time. Here we need to be careful with the cross product. dl over dt is equal to mr cross product dv dt plus dr dt cross product v. Because dv dt is the acceleration, we can substitute this, and also as dr dt is the velocity, we also substitute this. We end up with dl dt equal mr times a plus v times v. But this latter term is the cross product of two vectors that are parallel. This term is 0, and we get the simplified result that dl dt is equal to mr cross product a. We can rewrite this with the mass by the acceleration, which happens to be the force. So the derivative of the angular momentum with respect to time is r cross product f. But this is the definition of torque. We can then say that in the absence of a net torque, the angular momentum is conserved. And this is a very powerful result. I don't know if you have ever heard that strong earthquakes change the duration of the day on Earth. This is in fact true, although by a very small amount. What happens is that the mass at the crust of the Earth is redistributed. This changes the moment of inertia of the Earth. This changes the r in the angular momentum. Therefore, a change in p is in order. Because the redistribution of mass does not change the actual mass, we end up with a change in the angular velocity of the Earth by a very, very small amount, something like a couple of microseconds per day. Think now about the Earth revolving around the Sun. Do you know that the trajectory is an ellipse? You also know that both the Sun and the Earth actually are revolving around a common center of mass, which is a few kilometers from the center of the Sun. In our summer, the Earth is about 3 million kilometers farther from the Sun than in winter. If you look at the equation of the angular momentum with respect to the center of the trajectory, this means that r is greater in the summer than in winter. Because the force from the Sun on the Earth is parallel to the vector position from the center of the Sun to the Earth, there is no torque on the system. Therefore, the angular momentum has to be conserved. And this means that the Earth travels faster when closer to the Sun than when farther from the Sun. Let's do some math with this. Let's calculate the angular momentum of a cannonball following a projectile motion. I will calculate the angular momentum of the ball with respect to the origin. Initially, because the position is 0, there is no angular momentum. But I know that along the trajectory the ball will have some non-zero position vector and some momentum non-parallel to r, so there will be some angular momentum. I can anticipate now that here angular momentum is, with respect to the origin, is not going to be conserved. The vector position is written as x and y from the projectile motion gives us this pair of equations. For the velocity we need only to derive these equations. I will now calculate the cross product of r times p and substitute x, y, vx and vy. This leaves us with an angular momentum equal to minus 1/2 mv naught x gt squared k hat, which is clearly not constant as it depends on time. But we have previously seen that angular momentum is not conserved when there is an external torque. In this case, we should calculate the derivative of angular momentum. Which here is equal to minus mv naught x g t k hat. From our previous result, this should be equal to the torque. To calculate now the torque, we need to multiply r cross product F. Here the force is the force of gravity, minus mg j hat. Let's do this cross product now. This gives us minus mg v naught x t k hat, which is just the derivative of the angular momentum with respect to time. Fantastic, right? May the science be with you.